August 12, 2000, the Barents Sea. It was the Northern Fleet's biggest major exercise in more than a decade, a massive display of post-Soviet power involving roughly 30 ships and several submarines. Leading this armada was the K-141 Kursk, an Oscar II-class nuclear-powered cruise missile submarine. She was an apex predator of the deep, a double-hulled Leviathan designed specifically to hunt American aircraft carriers. She displaced over 18,000 tons submerged and carried enough cruise missiles to level a fleet. But at 11:28 in the morning, the physics of war were replaced by the volatile chemistry of a faulty weld. Inside torpedo tube number 4, a Type 6576. A hydrogen peroxide torpedo sat waiting to be fired. This weapon did not use stable batteries. It was fueled by kerosene and a volatile oxidizer known as high-test peroxide. For 50 years, naval engineers had feared high-test peroxide. When it comes into contact with certain metals, rust, or organic material, it decomposes instantly, expanding its volume 5,000 times in a fraction of a second. At that specific moment in the torpedo room, a microscopic crack in the casing allowed the peroxide to weep onto the grease of the torpedo tube. The result was immediate thermal runaway. A chemical explosion on the order of 100 kilograms of TNT blew the heavy steel door off the back of the tube. The blast was survivable for the ship, but it ignited a fire that burned at temperatures hot enough to melt steel like wax. For exactly 135 seconds, the crew in the forward compartment fought a desperate battle against a jet of fire. They were trying to prevent the unthinkable. They failed. At around 11:31 in the morning, the heat inside the torpedo room reached the point where the stored warheads began to cook off. Multiple torpedo warheads detonated, producing a blast on the order of 2 to 3 tons of TNT. The physics of an underwater explosion are distinct from those in the air. Water is incompressible. It does not absorb shock, it transmits it like a solid piston. The blast wave traveled through the length of the submarine with the force of a hydraulic hammer, shearing bulkheads and ripping the 2-inch thick pressure hull wide open. The explosion registered on seismographs across northern Europe as a seismic event reported between 3.5 and 4.2. This was not a sinking, it was a violent slamming of the vessel against the seabed. The pride of the fleet impacted the silt at a depth of 354 feet, digging a trench with its momentum before coming to a rest. Silence returned to the Barents Sea, but the clock had already started ticking on one of the most complex engineering challenges in maritime history. For the first few days, the world hoped for a rescue. But days later, as rescue divers worked the aft escape hatch, the grim reality settled in. The interior was flooded, the crew was lost. The mission objectives shifted immediately from humanitarian rescue to strategic containment. The Kursk was now a nuclear hazard sitting in international fishing waters. She contained 2 nuclear reactors and 24 shipwreck cruise missiles, weapons designed to be capable of conventional or nuclear warheads. Leaving her on the bottom was impossible. The Russian government declared a salvage imperative. They needed the hull recovered, and they needed it before the harsh Arctic winter locked the ocean under ice. The initial surveys brought back data that made seasoned salvage masters pale. The submarine was not just resting on the bottom, she was embedded in it. The Barents Sea floor is composed of a fine, silty clay that acts like industrial glue. When a heavy object sits in this sediment, the water is squeezed out from underneath, creating a near-perfect vacuum seal. To lift the Kursk, the engineers would not just be fighting the mass of the submarine, they would be fighting the seabed's grip as well. They would be fighting the suction of the seabed itself. Preliminary calculations suggested that breaking the mud seal could add thousands of tons of extra breakout force. If they applied that much tension to the lifting cables, the hull of the submarine would not rise. It would tear apart, spilling its nuclear guts into the current. The engineers realized they needed a plan that defied the conventional laws of buoyancy. They had to lift the unliftable, and they had to do it without breaking the spine of a dead ship. The engineers ran the numbers, and the equation returned a fatal error. The model said it would take roughly 9,000 tons of traction just to break the submarine free of the seabed. But in the world of deep ocean salvage, gravity is often the least of your problems. The real enemy was a variable known as breakout force. The Kursk was resting on a seabed composed of compacted silt and clay, a geological paste that had formed a vacuum seal along the entire 505-foot length of the keel. The friction coefficient of this clay meant that the initial force required to pull the submarine free was not 9,000 tons. Public figures vary, but the breakout force was expected to be far beyond the submarine's simple lift weight. This number presented a physical paradox. There was no crane vessel in existence capable of exerting 25,000 tons of straight vertical lift. Even if such a monster existed, the submarine itself could not survive the tension. The Oscar II class was built to withstand the crushing external pressure of the deep ocean, but it was not designed to withstand extreme tensile stress from above. If a crane simply hooked onto the hull and pulled with maximum power, the steel frames would shear and the submarine would tear into pieces, leaving the reactor compartment buried in the mud while the lifting cables came up with nothing but scrap metal. The salvage masters from the Dutch consortium, Mamoe and Smit, realized they were not just lifting a ship, they were trying to peel a piece of tape off a glass table without tearing the tape. To solve this, they had to understand the specific geometry of the disaster. The divers sent down to survey the wreck reported a chaotic crime scene. The visibility was often less than 10 feet, obscured by the silt stirred up by the bottom currents. Through the gloom, they mapped the devastation. The entire bow section, the first compartment, was a mangled ruin of twisted steel ribs and torn plating. It looked less like a ship and more like a car that had gone through a crusher. This structural weakness meant the bow could not support its own weight during a lift. It acted as a dead anchor, dragging the rest of the ship down. The engineers realized that before they could even attempt to fight the suction of the mud, they would have to perform a radical surgery. They would have to amputate the head of the beast. The challenge of the mud suction required a change in tactics. They could not use the standard salvage method of passing heavy chains or slings underneath the hull. Tunneling under the submarine to thread these chains was deemed too dangerous. The seabed was unstable, and the risk of the hull shifting and crushing a diver or pinching a hose was too high. Furthermore, chains would squeeze the hull inward, potentially cracking the pressure vessel and releasing radiation. The hull had to be lifted from the top, not cradled from the bottom. This meant the lifting force had to be distributed perfectly across the ship's center of gravity. The plan that emerged was a feat of geometric brilliance. Instead of fighting the mud all at once, they would trick it. They would lift the stern of the submarine first, peeling it off the seabed at a slight angle. This would break the vacuum seal at the rear, allowing water to rush underneath the keel. Once the water pressure equalized under the hull, the suction would vanish and the lift weight would drop back down to the manageable 9,000 tons. But to execute this delicate maneuver, they needed a connection point that was stronger than steel cables and more precise than chains. They needed to turn the submarine's own structure into the lifting mechanism. They needed to drill directly into the pressure hull. The decision was made to use 26 high-tensile lifting strands, each capable of bearing 900 tons. But there were no hooks on the Kursk to attach them to. The engineers would have to manufacture their own attachment points. They designed a system of expanding clamps that would function like massive drywall anchors. These clamps, known as grippers, would be lowered into holes cut specifically into the submarine's thick steel hide. It was a plan that required millimeter precision in an environment where the water temperature was 34 degrees Fahrenheit and the pressure was 160 pounds per square inch. The theoretical physics were sound, but the practical application required a machine that had never been built. They were about to turn a salvage barge into a massive, computer-controlled puppet master, and the strings were made of steel. To save the hull from collapsing under its own weight, the engineers realized they had to violate the most basic rule of submarine safety. They had to deliberately breach the pressure hull. The structural integrity of the Kursk was compromised, and wrapping chains around it was akin to squeezing a soda can. It would simply crumple the sides. Among the strongest remaining points were the massive vertical bulkheads and the thick steel ribs of the frame itself. To access them, the salvage team decided to cut 26 distinct holes directly through the rubber and steel skin of the nuclear submarine. It was a logical paradox. To salvage the vessel intact, they first had to damage it further. The machine chosen for this surgical procedure was not a traditional crane ship. Cranes are susceptible to the pendulum effect. A heavy load swinging on a cable can capsize the lifting vessel. Instead, the engineers deployed the Giant 4. This was a massive, semi-submersible barge, a football field of flat steel that served as a floating platform. It was a massive semi-submersible deck barge, towed into position and held on station, and its deck was modified to host 26 hydraulic strand jacks. Unlike a winch that winds a cable around a drum, a strand jack works like a person climbing a rope, hand over hand. 2 sets of hydraulic grippers work in unison. The bottom set holds the cable, while the top set slides up, clamps down, and pulls the load up by the length of a hydraulic piston stroke. It is slow, rhythmic, and infinitely powerful. The connection point between these hydraulic muscles and the sunken submarine was a piece of custom engineering known as the gripper. Imagine a massive steel toggle bolt, similar to what you might use to hang a heavy shelf on a hollow wall, but weighing several tons. The design called for divers to lower these plugs into the 26 holes cut into the submarine. Once the gripper was inside the pressure hull, its arms would hydraulically expand outward, locking against the underside of the thick steel deck. This created a mechanical connection that transferred the lifting force directly to the submarine's strongest structural frames, bypassing the fragile outer skin entirely. Executing this connection required a level of underwater precision that bordered on the impossible. Saturation divers, living in pressurized chambers for weeks at a time, descended to the wreck site. Their first task was to carve the entry points. They used high-pressure abrasive water jets to slice through the thick rubber anechoic coating, tiles designed to absorb sonar, and then through the high-tensile steel of the outer hull. Once the holes were cut, they had to install massive steel guide rings on the hull. These rings acted as funnels, ensuring that when the giant four lowered the heavy grippers from the surface 300 feet above, they would slide perfectly into the holes despite the blind darkness and the shifting currents. But the interface had one final invisible enemy: the waves. The Barents Sea is never truly calm. Even a modest swell could make the giant four heave up and down. If the barge rose while the cables were tight, the sudden jerk could shock-load the system, snapping cables or ripping grippers out of the submarine's deck. To neutralize this, each strand jack was mounted on a pneumatic heave compensator. These were massive banks of nitrogen gas cylinders that acted as shock absorbers. As the barge rode up a wave, the nitrogen compressed, paying out cable to keep the tension on the submarine constant. It was a dynamic breathing system designed to decouple the violence of the surface from the stillness of the bottom. The interface was ready, the lifting system was calibrated, but as the engineers ran the final simulations, the computer models flagged a catastrophic variable located at the front of the ship. The winter storms of the Barents Sea obey a strict schedule. By late October, the window for safe operations slammed shut, replaced by gale-force winds and waves capable of snapping steel cables like cotton thread. The salvage team had only a matter of weeks before the weather turned lethal. But as the engineers reviewed the structural data from the bottom survey, they realized they had a massive problem. The explosion in the torpedo room had not just destroyed the bow, it had transformed it into a chaotic pendulum of jagged steel. The first 65 feet of the submarine were a structural ruin. If the giant four attempted to lift the Kursk intact, this mangled nose section would hang unpredictably. It risked breaking off during the ascent, creating a sudden shift in weight that could destabilize the barge or shockload the rear cables, causing a catastrophic cascade failure. To save the body, they had to sacrifice the head. The decision was made to sever the submarine between the first and second compartments. This meant sawing through the entire diameter of a double-hulled nuclear cruiser while it lay submerged at roughly 370 feet in freezing water. They could not use explosives, as the shockwaves might damage the nuclear reactors in the rear. They could not use divers with torches, as the radiation risk and the sheer thickness of the steel made it physically impossible. They needed a machine that combined the precision of a scalpel with the brute force of a demolition ball. The engineers deployed a custom-built robotic cutting system. This was not a circular saw, but a massive reciprocating cable saw. The mechanism consisted of 2 heavy towers anchored to the seabed on either side of the submarine using suction piles, large steel cylinders that sucked themselves into the clay to create an immovable foundation. Strung between these towers was a heavy-duty cutting cable fitted with circular bushes coated in a special abrasive material. The system worked like a giant lumberjack saw, pulling the cable back and forth across the top of the submarine, slowly grinding its way down through the outer hull, the piping, the cabling, and finally the pressure hull itself. The process was agonizingly slow. The cutting cable had to chew through high-tensile naval steel and the submarine's outer coatings. Progress was agonizingly slow, a grinding fight against a structure built for war. When the system wore down, the team had to halt, reset, and keep cutting in the blind darkness of the deep. It was a battle of attrition against the material science of the Cold War. The Oscar II class had been built to be indestructible, and it was proving that claim true even in death. After days of grinding, the sensors indicated the cut was nearly complete. But the most dangerous part of the anatomy remained, the keel. The keel is the spine of the ship, a reinforced beam of steel running along the bottom designed to take the weight of the vessel during dry docking. If the saw failed to sever this final ligament, the entire salvage operation would fail. The lift would begin, the hull would bend, and the submarine would dangle by a single strip of metal before snapping violently. The engineers pushed the hydraulic pressure on the cutting rig to its limit. The cable groaned against the keel. Then suddenly, the tension dropped. The resistance vanished. The nose of the submarine fell away onto the seabed, separated forever from the fuselage. The operation was now entering its terminal phase. The 26 lifting cables were tensioned. The grippers were locked into the hull. The bow was gone. The mathematics of the lift were sound, but the physics of the seabed were about to be tested. The engineers were staring at the suction variable. They had to pull the ship free from the clay without ripping the grippers out of the deck. They needed to apply thousands of tons of force, but they had to do it with the gentleness of a surgeon. The pumps on the Giant 4 began to whine. The pressure gauges climbed. The cables grew taut. For a long moment, nothing happened. The sea refused to let go. October 8, 2001. The control room of the Giant 4 was silent, save for the hum of cooling fans and the rhythmic thrum of the hydraulic power packs on the deck outside. The command was given to initiate the lift. This was not a manual operation. No human hand touched a lever. The complexity of balancing 26 separate lifting points, each carrying a different load and compensating for different wave intervals, was beyond human reaction time. A central computer system took control of the strand jacks, sending digital signals to the valves to begin the slow, piston-like stroke of the recovery. The first phase was the most critical. It was known as the breakout. The engineers watched the load cells on the monitors with obsessive intensity. As the jacks pulled the slack out of the cables, the tension readings began to climb. The tension readings began to climb through the thousands, rising in steady steps on the monitors. The weight of the submarine was now fully suspended on the cables, but the depth gauges showed zero movement. The Kursk was still glued to the bottom. This was the moment of maximum danger. The system continued to increase the tension, pulling harder against the suction of the clay. If the calculations were wrong, if the suction force was greater than the tensile strength of the steel strands, the cables would snap like whip cracks, potentially destroying the barge and dropping the submarine back into the abyss. The plan relied on a specific geometric maneuver. The computer was programmed to apply slightly more tension to the stern cables than to the bow cables. The goal was to peel the submarine off the seabed from back to front, breaking the vacuum seal incrementally rather than all at once. The tension climbed higher, pushing toward the edge of what the math said the steel could take. The steel strands were singing under the strain, stretched tight as piano wires. Suddenly, the sensors registered a shift. The stern broke free. The vacuum collapsed. Water rushed into the space between the keel and the mud, equalizing the pressure. The resistance on the gauges dropped instantly as the grip of the seabed vanished. The Kursk was flying. The ascent was a slow, majestic, vertical transit. The strand jacks settled into their rhythm, pulling the submarine up at a speed of roughly 30 feet per hour. It was a tedious industrial ballet. As the submarine rose through the water column, the external pressure against its hull decreased. This caused the air trapped inside the few surviving compartments to expand, changing the buoyancy of the vessel in real time. The computer system had to constantly adjust the hydraulic pressure to keep the load balanced. The pneumatic heave compensators breathed in and out with the swell of the sea, keeping the tension steady on the roughly 9,000-ton load, even as the barge pitched in the waves. For hours, the lift continued in the darkness. Radiation sensors mounted on the lifting cables monitored the water for any sign of a leak from the reactors. No abnormal spike was reported, and the monitors held steady as the lift continued. The double containment of the Oscar II class was holding. As the submarine approached the surface, the final challenge awaited. The Giant 4 had been modified with a massive recess in its hull, a cradle designed to receive the curved back of the submarine. This was the mating phase. The submarine had to be pulled tight against the bottom of the barge, locking the two vessels together into a single hydrodynamic unit for the tow back to port. The proximity sensors beeped as the conning tower of the Kursk cleared the keel of the barge. The massive rubber-coated steel hull rose until it touched the custom-fabricated saddles. The strand jacks applied a final locking tension, pulling the submarine firmly into the embrace of the Giant 4. The two vessels were now one. The operation had defied the odds. Through a combination of brute hydraulic force and delicate computer algorithms, they had recovered a nuclear leviathan from a depth of about 350 feet, roughly 110 meters. The Barents Sea had lost its prize. The engines of the towing tugs roared to life, churning the water white. The long journey home to the Kola Peninsula began, not as a rescue mission, but as a funeral procession of steel. The journey back to the coast was a slow, somber funeral procession. The tugboats kept the speed low to prevent hydrodynamic drag from destabilizing the massive load suspended beneath the barge. On October 21, 2001, the convoy arrived at Roslyakovo, a restricted naval settlement near Murmansk. Here lay the final hurdle, the floating dry dock PD-50. This was one of the few floating docks large enough to take the Giant 4 with the Kursk beneath it. But physics had one last card to play. The draft of the barge, combined with the submarine hanging beneath it, was too deep to clear the floor of the dry dock. The engineers had to bring in massive steel pontoons to add buoyancy, lifting the entire assembly just enough to clear the dock's sill with little room to spare. Once inside, the sea valves of the dry dock were closed. Enormous pumps began to drive the water out. For the first time in 14 months, the Kursk began to feel the air. As the water level dropped, the Giant 4 lowered the submarine onto the cradle blocks arranged on the dock floor. The strand jacks were slackened, the grippers were released, and the barge was floated out, leaving the submarine alone in the wet gloom of the dock. Then, the final drainage began. As the water receded past the conning tower, the true violence of the disaster was revealed to the world. The hull was not just broken, it was scorched. The rubber acoustic tiles were peeled back like burnt skin, revealing the high tensile steel beneath, heat discolored and scorched by the fire. The most chilling sight, however, was the front of the ship. Where the bow should have been, there was only a ragged, gaping maw of twisted metal. The cut made by the robotic saw was clean and surgical, contrasting sharply with the chaotic wreckage of the torpedo bulkheads. Inside this blackened cave, the investigators would later find the evidence that confirmed the sequence of events, the shattered remains of the torpedo tubes and the forensic signatures of the hydrogen peroxide explosion. But before the technical investigation could begin, a more sacred duty had to be performed. Teams of specialists in protective gear entered the hull to recover the remains of the 115 crew members who were still entombed inside. It was a grim, silent operation that stretched through the weeks that followed. The salvage of the Kursk rewrote the textbook on heavy marine engineering. It proved that massive objects could be recovered from cold, 100-meter depths using computer-controlled hydraulics rather than brute force. The operation was a complete technical success. The two nuclear reactors were inspected and found to be perfectly intact. The automatic shutdown systems had worked exactly as designed, preventing a radiological catastrophe that could have poisoned the Barents Sea for decades. The cruise missiles were unloaded from the hull in the weeks that followed. The hull was eventually cut up for scrap metal, its warfighting days ended by the cutter's torch. As for the bow section, it remained on the seabed until September 2002. It was deemed too dangerous to lift due to the potential presence of unexploded torpedoes. In a final act of containment, the Russian Navy returned to the site and blew up the remnants where they lay. It was meant to eliminate any remaining ordnance and keep the debris from ever surfacing. The site is now just coordinates on a chart, a patch of churned clay in the cold dark of the Arctic. The K-141 Kursk was gone, but the engineering feat required to bring her home stands as a testament to the cold, hard logic required to solve the impossible problems of the deep.